Hi there. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. Lovely to have your company again. Coming up in this episode, we're going to look at the HERA mission, which was launched not so long ago, but now they've reached some critical points in the mission, even though it won't reach its destination for quite some time. They've done some critical burns to get the thing moving in a more expedient fashion, let's say. We're also going to look at black holes, well, not specifically, but black hole echoes and how they might be able to be found using light. And speaking of light, this is a really interesting story about the human history of using light to treat people's ailments. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here again, see what I did there, is Professor Fred Watson. Hello, Fred.
Oh, you should be on radio, Andrew. Such good stuff that you do.
But no, I think 40 years on radio was enough. Although, you know what? I'd go back tomorrow if anyone asked. Oh, don't tell Judy. Don't tell Judy. But I would. Yeah, it's just good fun. I loved being on the air and telling silly stories, and got a big kick out of breaking news. If something big happened and no one else knew about it, I know that sounds pretty morbid because sometimes it wasn't good news, but breaking a story as a journalist is always a big, it makes you feel good. Sometimes. I better qualify that. It's not always.
No, I know what you mean. What you mean, yeah. It's interesting, yes.
Yes. We have plenty. This is a really fascinating episode, Fred, because we're talking about firstly the HERA mission, but I'm really interested in the two different stories about light, and because we couldn't do without light for many, many reasons. So we'll get into that. But the HERA mission, we didn't really talk about it when it first started because it started as a rocket launch, and what can you say? It launched. Okay, we got that done. But now HERA has reached a critical point, and they've done a fairly significant burn to get it into an accelerated approach to Mars, where it will do a gravity assist, and then that'll pick it up even more. But I think they've got to do another burn before that because they've got to adjust its course to get on target. We might start, though, by talking about what the HERA mission is all about. It's got two sort of objectives. One's a minor objective, taking advantage of the Mars visit.
Indeed, that's right. So it's in fact, it'll be really interesting. And that flyby that we're about to talk about is March next year. It's not very far down the track. So we've got a close approach to Mars. And it's a gravitational assist. That's why it's basically happening. But it will come within 300 kilometers of the surface of Deimos, which is Mars's smaller moon. If I remember rightly, it's about 14 kilometers across. It's a tiny world. And this will give us some really good close-up images of the surface of Deimos, which has been explored already by some of the orbiters that are around Mars. But that is HERA is going to give us another look. And just to tie up the details, you've sort of mentioned this already, but the reason why we're talking about this and why it's sort of in the news is because of this trajectory correction. So it's an ESA mission. I didn't mention that at the beginning. European Space Agency launched 7th of October, so very recently. But towards the end of October, on the 23rd, as you said, it underwent course correction. And the details are that it fired all three of its orbital control thrusters for 100 minutes. That's a long burn. And it changed the velocity by 146 meters per second. And then there was another one carried out just a few days few days ago. I'm not sure. Yes, from where we are now, it's 4 days ago. It was on the 6th of November. That lasted 13 minutes and put in an additional 20 meters per second. And now we've got it absolutely on track for the gravity assist at Mars in March 2025. So something to look forward to that we will almost certainly talk about next year.
Yes, indeed. I'm just trying to look up what its actual speed is total, but I'm having trouble finding it. But it's going hell for leather. Let's just say that.
Yes. So there's a further burn coming up a little bit later this month, Andrew, on 21st of November, which the mission scientists say will be it will be another correction of just a few tens of centimeters per second. So it's less than...
Isn't it amazing?
Yeah, it's just incredible what these guys can do.
I read, I think, that the telemetry that they're gathering so that they can make the adjustments includes 3 locations on the surface of the Earth, and one of those is in Australia. Is that right?
Yes, that's right. ESA does have it's got a tracking station in Australia. I think it's the new Norcia one. But I might be wrong with that. But there is an ESA tracking station here.
Now, it's going to take a closer look at Deimos, which is of great interest, given that it could become crucial in terms of future visits to Mars. It might provide some kind of. Is it the one that's going to actually fall back into Mars at some stage, or is it the other one?
That's Phobos. Yeah, Phobos is kind of spiraling slowly downwards towards the surface of Mars. I think Deimos is going the other way, actually.
Right. Oh, okay.
Yeah.
And is the thinking that they used to be like they captured asteroids?
Yes, probably. They're odd worlds. Phobos it's got the density of a piece of pumice. It's made probably 50% of it is empty space, which is really interesting. So that Phobos will be an interesting world to visit. And you might remember, it's probably now at least a decade ago, there was a mission to Phobos, which was launched by the Russian Space Agency, Roscosmos. It was called Phobos Grunt, and Grunt was the word for ground, because it was going to land on Phobos, but it didn't make it. The launch vehicle didn't give it enough orbital velocity, and sadly it burned up in the atmosphere, in the Earth's atmosphere, not Mars's. So yes, you're right. There's all that happening, and then there is the mission. The mission's real, its real goal, which is to go into orbit around Didymos. So it will actually orbit its target when it gets there. And by the way, the target date, the date for orbit insertion around Didymos is the 14th of December, 2026. That's my birthday, so that'll be a good thing to celebrate.
Wonderful.
The questions that it will really be interested in are not so much to do with Didymos, the asteroid, but its moon, Deimos, which is, if I remember rightly, about 170 meters across. And that's the one that the DART mission impacted in 2022. So the questions that HERA will be asking are things like, did it leave a crater? Or did it just sort of rebuild the whole asteroid? Because we think Didymos is a rubble pile. We think, Didymos is probably a rubble pile as well, but we think Dimorphos is a rubble pile. And a little bit more about its internal structure, which you'll be able to get from the details of the orbit that HERA finally goes into. So I think it's going to be a very interesting mission that will be a really neat follow-up for the DART mission, and will give us more information again on, all relevant stuff if ever we are under threat from an asteroid impact, because this is knowledge that we really need.
Yes, absolutely. And the good news about this mission is that it's not going to be that long down the track. Some of the missions that are headed out at the moment are just going to take so long. But this one, we're looking at just a bit over 2 years before we reach the destination, which in astronomical terms is a pretty quick trip.
Yes, it's if my calculations are correct, it's less than 2 years.
Less than 2 years.
Oh, yeah. Hang on.
No, I beg your pardon. No, you're right.
No, sorry. It's 2020.
My mum, you're quite right. Yes, it's a bit over 2 years exactly. Sorry, I'm miscalculating there. I'm putting my Marches where my December should be.
And I believe, I would think that Marie Claire, one of our most dedicated listeners, who went to NASA for that particular impact event of the DART mission, she'll be pretty keen on what happens next. So, and I've got all my DART memorabilia here. I've got my DART T-shirt, my DART stickers are over there, and thanks to Marie Claire, and hello to you. Thanks for your support. And it'll be a pretty exciting mission for all those involved, even those that were invited just to watch. Terrific. So, we will definitely be updating that when the time comes. And if you want to read the story about the course adjustment and the mission, the HERA mission, it's at the phys.org website, PHYS. Now you're with Andrew Dunkley and Fred Watson. This is Space Nuts.
Roger, you're loud and clear here also.
Space Nuts.
Now we've got a couple of light stories. They're either light stories or light stories, depending on which way you want to look at it. This first story, Fred, brings us back to our old favourite topic, black holes. But I found this story interesting because it really explains well how light is affected by gravity, particularly the gravitational effect of black holes in space, and how we can witness events more than once because of this. We've talked about that before, and they refer to them as light echoes, do they not?
Yeah, they do. And light echoes are sort of a broad topic in astronomy. We've got a situation where, because of the finite speed of light, you can sometimes see the same event twice. Perhaps the classic one is, and the one that's easiest to get your head around, is if you have a supernova explosion, a star explodes, and you get the direct beam of light that comes to us that tells the story of the explosion. But sometimes you get reflections off dust clouds, which is quite often a long way away from the supernova explosion, so that the light takes a dogleg path. And eventually we see it again. And that's actually one of the ways why we can sometimes see supernovae which exploded in historical times. The one that I like is Kepler supernova, which took place in 1604, and we can still see it because of a light echo. So you can analyze modern equipment to analyze the light. This is something a little bit different. I'm going to pause for a minute, Andrew, because there's a gentleman with a what I would call a strimmer and you'd call something else, is doing the grass out the back of our house. Are you getting any noise interference there?
Oh, just a little bit. It's not too bad.
Okay, I'll keep going then. I keep going. So with the black hole story, it's not about reflections from dust clouds. It's about refraction, about the light being bent by gravity around the black hole. So the intense gravitational field of a black hole pulls light around it, and it will either deflect it slightly, or depending on where the light is emitted, or it can be something that goes all the way around. And in fact, it can go all the way around more than once. And so the paper that we're talking about, which is, I'm looking at the original paper here in Astrophysical Journal Letters, is called Measuring Black Hole Light Echoes with Very Long Baseline Interferometry. And it's by a group of scientists who are all in the US, at institutions with very, very prestigious names, like the Institute for Advanced Study in Princeton, which I think was where Einstein worked, the Los Alamos National Laboratory in New Mexico, all of these places. And so this is something, it's work of a very high quality. What these authors are suggesting is that if you have... So think of a black hole. Around it, it's got the accretion disk, the disk of material that is swirling around the black hole, some of which is actually going to disappear inside it, and some of it will be squirted upwards along the relativistic jets think of that accretion disk. That's got stuff in it that's swirling together, and just basically the energies that are involved are such that you get X-rays and radio waves coming from that accretion disk. Now, if you imagine, a particularly big lump of something in there that hits another particularly big lump in that disk, you're going to get a flash, basically an explosive event which will release radiation. And the point that these authors make is that radiation, yes, may take a direct path towards the Earth, but it could also go around the black hole, and it could go around multiple times. So you might get an explosion that we see, and then a number of light echoes that follow it at sort of pretty regular intervals as the light travels around the black hole. And so what they've suggested is that if you can analyze that and look at it in detail with radio telescopes we're talking about here, because that's the waveband that's of interest in this, then that might tell you something about the details of the accretion disk and the events that are taking place inside it. If you could see, whereabouts these light echoes seem to come from and things of that sort. And what they're suggesting is that you could do it with this technique called Very Long Baseline Interferometry, or VLBI, which is beloved of radio astronomers. And what you do is you have dishes separated by large distances, and you can sort of correlate the signals that each gets because they're slightly different, because of the separation of them. And that lets you essentially see very, very fine detail. It's actually how the Event Horizon Telescope works, the thing that has indeed mapped the event horizon of several supermassive black holes. So, the bottom line is you can't actually do it with very long baseline interferometry on Earth. You need to put you can do it with one telescope on Earth, but you need to put one of them in orbit around the Earth, or at least into space. You need the distances that you get from putting the antennas that are going to provide the baseline. You need to put them very, very far apart, and so it's a paper that suggests how you might do that. I've just got the abstract from the paper in front of me. What they say is our results suggest that detecting echoes may be achievable through interferometric observations with a modest space-based very long baseline interferometry mission. So modest is a word that you can put numbers on, and I think the numbers are later in the article. I haven't actually read the paper itself, but in the abstract they certainly talk about the kinds of effects that you might see and what you might need to build in order to do that. Now, interferometers in space are not a new suggestion, so it may well be
some of our audience have suggested it.
They have indeed. That's right. They have indeed. So we might find that this is something that almost that the hardware already exists, because there are radio telescopes in space already. But anyway, they're suggesting they're not really going into detail of how you might do it, but they're suggesting that it will in fact be possible.
Okay, so we are not there yet, but they've certainly looked at ways that they might be able to do this by through publishing this paper. They've gone public on it.
That's exactly right. Yeah, what they concentrate on in the paper is the details of this, this multiple apparition of flashes of light, and the actual how the gravity of the black hole actually steers the light around, and just the details of what the black hole might do to the light. And by light, I'm talking really here about radio radiation, and suggesting that you might need bigger tackle than we've got already in order to measure it.
Yeah, what fascinated me in the story is how you talk about an event collision that creates a flash, and that light comes straight towards us, and we see that event. But the light can also be disrupted by the gravity of the black hole and do a few laps around the black hole before it gets headed in our direction. So what sort of a time difference would it make between us seeing the real event and then the echo?
Well, they'd be very small, wouldn't they? It's going to depend on the size of the black hole. I think they're talking about supermassive black holes. And in fact, their article talks about, we explore the viability of our method using numerical general relativistic magnetohydrodynamic simulations. There you are. Of a near face-on accretion system scaled to M87-like parameters, M87 being the galaxy of which we've imaged the supermassive black hole at the center. And so you're talking there about an event horizon that is solar system sized or much bigger than the solar system. So you're talking about possibly hours to days of delay in the difference.
Still, that's a short time frame in terms of being able to collect data. So that's it makes it even more. Gee, they're doing a good job in your backyard by the sound of it.
Yeah, I'm wondering whether I'm going to have to move, Andrew, to find quite a place to do this. So let's move house, and we'll keep going. We'll keep talking, but I'm going to take you with me and find a quieter part that helps to do this.
This doesn't happen often, but
no, it's all about. Yeah, no, that's right.
That's a
I'm just going to wander around this way because I think it'll be quieter right at the other end of the house.
Right. Just depends whether or not you lose your Wi-Fi connection in the process.
Shouldn't do. Hopefully it should be all right. So I'm now in Marnie's study, which is currently taking service as a bedroom because we've got lots of visitors coming. So here we are.
Oh, very nice. Oh, nice view. Beautiful. Excellent. Very good.
So it's silent. Look at that. Complete silence.
Yeah, until they come around the corner and do that bit.
That's
Yes, but I think we've pretty well wrapped up that story. So if you are interested in reading it, it's in universetoday.com, or you can read the whole thing, Measuring Black Hole Light Echoes with Very Long Baseline Interferometry in the Astrophysical Journal Letters. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Finally, Fred, we continue our look at light, but this is light of a very different ilk, I suppose you could say, because it looks at the relationship between light and humans and how, even since ancient times, we've used light for medical purposes, which is fascinating. And this dates back a long, long time.
It does indeed. That's right. And, I guess I think, as you said, you've almost experienced this yourself. We all know that the sun is the principal source of heat and light for the planet. It's what allows life to evolve. It's where the energy comes from. And so it's not really surprising that our forebears of various different ilks should have had a special place for light in their understanding. And you've only to think of some of the civilizations in South America, which were based on sun worship. Talked about some of those. The reason why we're talking about this is a very, very nice conversation article that has recently been issued, the 7th of November, just a few days ago, written by Philippa Marta, who is a lecturer in pharmacology, women's health at the School of Biomedical Sciences in the University of Western Australia. And Philippa's written a lovely kind of overview of the part of light in making us better.
Yeah.
And her article is Part Science, Part Magic, an illuminating history of healing with light. A very nice title there. And it starts off with some of the most ancient religions on the planet, which involve sun worship, and takes it from there, because often these early religions were tied up with healing. And just reading from Philippa's article, sick people would turn to the shaman or priest or priestess for help, and that's, it's a natural thing to do when you kind of feel better when you're in sunlight. And so the article traces that history right through to more modern times, and the fact that we still use phototherapy with blue light used to treat newborn babies with jaundice in hospital, that sort of thing. Really interesting, and a really interesting story with a very comprehensive look at sunlight and its place in our well-being.
Yes, and when you talk about the ancient cultures that used to use it, and papers were actually written about it, dating back to 1500 BCE in Egypt. Egyptian medical scrolls have been discovered that talk about using sunlight mixed with other things to try and overcome certain frailties, illnesses, afflictions, whatever you want to call them. But even as simple as the warmth of the sun being used to heal, just simply getting warmer. And you probably could read some of this stuff and say, oh, look, it's all hogwash. They were obviously just, they didn't know much about medicine, so they came up with these lame brain ideas. But even today, light is used in medicine, and there are great examples of it. It doesn't so much happen in Australia, but there are parts of the world that get very dark and dreary in winter, and you can overcome that with certain forms of light. You can cure jet lag with light. You can, different kinds of light for different kinds of circumstances, white or blue light. When you expose people to that, it can overcome forms of depression in some cases. And you can use ultraviolet light to treat skin conditions. The article refers to that. It is quite a natural thing because we've grown up and adapted to sunlight as a species on this planet over tens of thousands of years. So it makes sense. And some of the interesting people that have talked about light have been brought up in this article. One of them was Florence Nightingale, who actually wrote did she write a book about it? Yeah, she wrote a book called Notes on Nursing, and was a strong believer in the power of sunlight. So this is quite incredible stuff. Sorry, go on.
No, go ahead. Go ahead, Andrew. That's fine.
Well, I was going to just sort of put myself out there because even though it's not directly sunlight related, we still use things that are created in the light spectrum to treat serious illnesses. And you look at radiation therapy for cancer. Well, the rays that are produced by radiation therapy type machines are in the light spectrum. So you could argue that we're still to this day in modern medicine using light. And you said earlier, Fred, that I have some experience with that, and a few people that listen to the show already know this, but I have been, for the last 2 and a bit years, been dealing with a cancer diagnosis. And over the last 5 weeks, I've been receiving radiation therapy for remnant cells caused by prostate cancer. And hopefully the therapy will be successful and eradicate them. So that's my personal experience with, if you want to call it, light therapy. It's not use of sunlight. These, in my case, would I've done some research because I need to know these things for it. But it's in my case, the form of therapy I'm receiving is actually using X-rays to attack the prostate cancer cells. And according to my oncologist, I'm a very, very good candidate for this kind of therapy. And it started off with an injection in the bum, which was a hormone suppressant to stop testosterone, which is what prostate cancer feeds on. And then that was 3 months ago. And then I started my radiotherapy 5 weeks ago, just after we got back from Turkey. And that finishes at the time of this recording tomorrow is my last dose. And then on Thursday, I get another hormone shot to stop the testosterone from recharging so that the radiation therapy's got the best possible chance of killing off the cancer cells. So, that's been my life for the last 5 weeks or so. And basically, I've been dealing with this for a bit over 2 years. So at the beginning of last year, I had the prostate removed, but the pathology showed that the cancer had broken through the prostate cell, wall, and got into a thing called the seminal vesicle. And this was probably the unlucky bit. When they took the prostate out, they severed the seminal vesicle. So 2 millimeters of cancer cells were retained in my body, and that's where it's all sort of come from. So, that sounds shocking. It sounds horrible. It sounds scary, and I suppose it is to a certain degree, but I'm dealing with it, and my prognosis is very good. Obviously, they can't give me absolute guarantees, but this therapy is the most successful available today. So, fingers crossed. But light therapy is a thing.
So you're right. The X-rays that you use are part of the electromagnetic spectrum, and so it's just light radiation with very short wavelengths. I think it's all credit to you, Andrew, for what you're going through at the moment, and for opening up to all of us space nutcases who are all very much interested in your well-being. And
I've received some nice messages. I went public through the Cancer Council New South Wales because I get a regular newsletter from them, and they put an appeal out for anyone who might be willing to tell their story in the hope that it will help others. So I, with my radio background, felt that was probably something appropriate. And I will give the same message right now. If you're a man, 50 or over, you need to go to the doctor and have a PSA check, and get them to check your heart, your diabetes, or blood sugar levels, and your cholesterol all at the same time to make sure you're okay, particularly PSA levels, because if they start to climb, they can look innocent enough, and then all of a sudden they will balloon. And that's what happened to me. I went from a 2.1 PSA level to a 7.8 in 22 months. And that's when they knew something was dreadfully wrong. So all it takes is an annual checkup at your local doctor just to see if everything's okay. And if you do that and you do develop prostate cancer, chances are they'll catch it super early and you won't end up where I am. So don't dilly-dally. It's not going to hurt you just to go and get a quick blood test and sort it all out. That's my message to any man or someone you know of the male persuasion, 50 or over. And I would take that back to 40 plus if there's a family history. There you go. All right. I've done my job.
Well done. Yeah. No, it's very good to hear.
Yes. I think it's an important message.
Indeed it is. Yeah. And it's all about light, as you say. It's all about light.
Yes, it is. Yeah. And it's a great story. Read it. It's at theconversation.com, and it's a really interesting story. Part science, part magic, and illuminating history of healing with light. It's a terrific story. Well worth reading. And we might just end it there. Fred, thank you so much.
It's a pleasure, Andrew. It's a temporary ending, of course, because we'll be coming back again.
Yeah. I'm not dropping off there. I'm not dropping out of the Twiggins hurry. Believe me.
When you said I'll end it there, it did sound a bit final. But
sorry about that. No, it's all good. Yeah,
it's all right. See you next time.
Indeed. Yes, we've got some questions to sort out in our next episode, so I do want to be around for that. Thank you, Fred. See you soon. Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio for not sending me any sick jokes this week. He does it all the time, and some of them are horrible. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode, guaranteed, on Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.